Alright, we resume. Guys, we know almost everything there is to know about functions now. With the power of differentiation, if I can take the derivative of a function, and I can take the derivative of pretty much any function I've seen so far, then, assuming I can analyze that derivative, I can know when the function is increasing, when the function is decreasing, and where there is a relative max and min. Yeah? Okay. Well, there's about one more thing, however, that that we haven't talked about yet, and that is the sort of curviness of a function. This is something which came up, I think, if you had Mr. Schaefer for physics, he calls it curvy up, curvy down. Does anyone remember what I'm talking about? Very, very, very vaguely. What is this whole curvy up, curvy down situation? Well, it's like the following. So take the function f of x equals x squared, but let's only look at it on the interval from 0 to infinity. And let's take the function f of x equals, I'll do this just below, how about f of x equals root x? Alright, well this function kind of does a little bit of this, and this function does a little bit of this. Alright, well, notice the similarities and differences of these two functions. They're both positive, so that's good. They are both increasing, true or false? True. They are both increasing. So what is it exactly, yet I feel there is some subtle and important difference between these two on some deep level. Can someone say something about them? And besides the fact that they're inverses of each other, all kinds of, that's not relevant. Lara?
Squared is increasing at an increasing rate, and root x is increasing at an decreasing rate.
Yeah. They are both increasing, but f of x equals x squared is increasing faster and faster. She said it even better. The rate at which it is increasing is increasing. Okay? And of course, what seems relevant, Emma, to the rate at which something is increasing?
The second derivative.
The second derivative. Because as the derivative measures the rate of change, the second derivative measures the rate of change of the rate of change. And do we all kind of agree with this? And over here, this function is increasing, but the rate at which it is increasing is decreasing. And yeah, again, the second derivative seems relevant, right? Because the second derivative is the rate of change of the rate of change. Okay, awesome. Would anybody like to give me a physics interpretation, perhaps, of this situation? If this is a position versus time curve, can I get an analysis of what is going on, maybe? First, tell me all the things that are the same. Raymond, tell me one thing that's the same about both of these.
Position is going forward, increasing.
Yeah, the position is going forward. In other words, if you have established some coordinate system in such a way that 0 is like home base, then both of these functions describe particles which are running away, right? Okay? So that's what, you want to keep going, Raymond, or should we constable? Let's keep going with Raymond. Raymond, keep going.
Still the same, or should I do it different?
More, maybe if you got more than the same.
Not. They start at 0.
Yeah, they
but the acceleration of the first one's bigger than the acceleration of the second one, because if you look at the slopes, or the slopes of the tangent lines for the instantaneous velocity, it's increasing on the first one and decreasing on the second one.
Yeah, maybe we could just use simple words, actually, instead of like, oh yeah, I agree with everything you said, but just using maybe simple common sense words for a little while. Of course, we know, because we've previously discussed this, that if I draw the tangent line to the curve, that's going to give me my instantaneous velocity. And so we can see what's happening to these tangent lines, what's happening to them? They're getting steeper, right? So yeah, in very informal terms, we would say that this guy is accelerating, right? He's accelerating, his velocity is getting bigger, yes?
So for like physics, that guy is like on a rocket ship that's going through space and he has the engine on, the other person's braking.
Yeah, you said that very, very fast, but yes, they're both moving with positive velocity, because these slopes are positive, but this guy's velocity is getting bigger. He's on a rocket ship, says Robbie Bush. Over here, if I draw the tangent lines to the curve, I can see that the slopes of those tangent lines are getting smaller and smaller. So this is something which is now slowing down. Cool? Okay. There was something else I was going to say about this.
Second derivative.
Yeah, the second derivative. So that we may learn the deep connections between these, perhaps what we should now try to draw, this is a little bit hard at first, and then it becomes really, really easy. Please draw me examples of 4 functions. Let's just, for simplicity's sake, let's just say that they should be defined on the defined on all real numbers, in such a way that in this picture, the derivative is positive, but the second derivative, and the second derivative is also positive. In this picture, the derivative should be positive, but the second derivative should be negative. This one, the first derivative is negative, and the second derivative is positive, and then this one, they're both negative. It's a little bit hard, unless this kind of stuff just comes to you recently. We've also done a couple homework problems that were kind of like this. Yeah, draw a function. If you want to give a name for a function too, you can do that. How's it going? Share with the person next to you.
Yeah.
Wait, is this on all real numbers?
I didn't try, I couldn't have like.
What's up?
It's on all real numbers or is it
I don't know. Yeah, I guess we could do it on all real numbers, right?
Yeah.
Or I don't know. I guess I'm not super picky about that.
But then what if they can see here, this is the second term, we can make it bigger.
The cubic effect.
well, the grade will be reflective of the one, so it happened to be worse than that.
Going down.
Okay.
Right? Terrible. I think it's like there's the one, like the first problem I should have gotten right.
Like,
So it's like, with the derivative, it's getting more negative and more negative.
I have to be accident for
Like one that can get
Okay. So what do you got? What is a function which is, well, the first derivative is positive, which kind of means what as far as the function's concerned? It is increasing, but also the second derivative is positive, which means the rate at which the function is increasing is increasing. So what's one function that does that?
X squared. Go from 0 to infinity.
Okay, yeah. Anything that's kind of shaped like this, like an exponential function will do that, right? For example. Yep. If we look at all of the tangent lines, we see that they are getting bigger and bigger. Okay, what's a function whose derivative is positive, but the second derivative is negative? That means that the rate at which the derivative is changing is negative. In other words, the derivative is getting smaller. What's a function that meets that? Root x, or maybe? Oh, you said root x? Yeah, maybe like I think like log x is a good example, right? Or some kind of just, I don't know, or something like just that, whatever that function is. I don't know. It's like upside down exponential is what that is, perhaps.
Yeah, -2.
Right here we have, is that right? Yeah. Here we have a function which is increasing, but the tangent lines to the curve have a slope which is smaller and smaller. All right. How about over here? The derivative is negative. The first derivative is negative, and this is where it gets a little complicated. So now I'm looking for a function which is decreasing, but the rate of change of the derivative is positive. Okay, well the rate of change of the derivative is it's whether the derivative is getting, so Ethan's got it. The second derivative, if the derivative is negative, then to say that the second derivative is positive is to say that the derivative is getting less negative. So what's in a function that does that? Yeah, like that, some kind of decaying exponential function will behave that way, right? Here the function's certainly decreasing, but if you look at the slopes of the tangent lines, the slopes of the tangent lines are getting bigger. Bigger in the sense of less negative. Magna, you cool? Okay. And then the last one, I want a function which is decreasing, but also the rate at which it's decreasing is decreasing. Yeah, I guess like an upside down version of that, right? No.
Upside down.
Upside down version of that.
Upside down version of that.
Yeah.
Yeah. Some kind of like that type function.
Logarithm.
This function is decreasing, but the rate at which it is decreasing, as measured by the slopes of the tangent lines becoming more negative, so to speak. Follow? Okay, so, what I have here is this notion of concavity. The concavity, and there are many different ways of defining this. Different textbooks do this differently. But basically, loosely speaking, we think of concave up functions as functions which look like this. They're concave up. And concave down functions kind of look like this. All right, this is a somewhat controversial definition of that to give you, but it is, I think, the best definition. Every textbook does this a little bit differently. There's no uniformity on this, but I like my way best. So I'm going to define concavity as a property that the function has. And I will now draw a concave up function. And I claim that the definition of a concave up function, the definition which we'll adopt in this class, is it is a function in which the tangent lines lie below the curve. Or if I want to be more precise about that, I should say a function is concave, the actual term is concave up. So f is concave up on some interval ab, if and only if, according to me, tangent lines to f lie below f on that interval. And as you can see, the tangent lines are lying below the curve. Cool? Okay, if a function has that property on an interval, we say the function is concave up. Conversely, a function is concave down if the tangent lines lie below the curve. Am I still in frame? The tangent lines lie below the curve. So I'll write that down. F is concave down on some interval a, b, if and only if the tangent lines to f lie below f. Above. Tangent lines to f lie above f. Okay. Awesome. All right. There's a story involving this. It's kind of a terrible story. It's not really a good. Well, I used to be really proud of it, but now lately, in recent years, people have rebelled against it. So it's all about elephants. You are in some remote hunter-gatherer society in which you are out with your tribe hunting elephants. And you catch an elephant. And there's hundreds of you in your tribe. You have not invented simple machines yet. So when you catch the elephant, you just have to carry him back to the village so that you can, eat him for a month or whatever. So when you want to carry the elephant, everyone crawls under the elephant, puts their hands up in the air. Everyone do it. Hands in the air.
I think it's that big.
Concave up. Hands up. To carry the elephant back into the village. And all of your little hands are all the little tangent lines which lie below the curve. The curve is like the elephant. We carry the elephant back into town. Alright, if you don't like hunting elephants because you think it's cruel, then you can pretend that the elephant got a splinter and you're carrying it back to the town doctor to take the splinter thing out. But nonetheless, concave up. What is concave? When you hear concave up, you should think concave up. Hands up in the air, under the elephant to carry the elephant back into town. All right, concave down. On the other hand, now what you have is now the elephant has stepped on a. This is the part where the elephant gets the splinter. So the elephant gets the splinter, and he's it doesn't make total sense. The elephant gets a splinter, and now he's like just crazy. He's having an elephant temper tantrum, and he's like going to destroy the village. So you have to calm him down. So all the villagers come, put hands on top of the elephant, concave down, hands down on the elephant, calming him down. Calm down, elephant. It's going to be okay. So get it? So concave down, hands down, tangent lines down, line above curve. All right, awesome. All right, that was pretty exciting, yeah. Good. Well, do we feel that there's some deep connection between concavity and the second derivative? Yes. I do.
Since you mentioned it, I do.
Yeah, tell me what kind of claim can I make, do you think, about the relationship between concavity and the second derivative?
Wait, yeah.
Yeah.
So when it's
the second derivative is negative. Let's just watch what is happening to the tangent lines. They're big positive, then small positive, then zero, then small negative, then medium negative, then big negative. What is happening to these tangent lines? They are getting smaller. Their slopes are getting smaller, right? The second derivative is negative. The second derivative measures the rate of change of the derivative. And if a function is concave up, second derivative is positive. And again, you can see that by just looking here at the tangent lines. They're huge negative, then medium negative, then small negative, then zero, then small positive, then medium positive, then huge positive. What's happening to those tangent lines? They are increasing, right? The derivative is increasing, so the second derivative is positive. Follow?
Yeah.
Okay. So we need to prove this. This is a theorem.
Oh my gosh.
And it's a pretty hard theorem, actually. How's it going over there?
Wait, he's doing?
No, they're graded. He's just doing some bookkeeping. All right. What we need to do is we need to prove this theorem. Here's what the theorem says. I think we can do this in like 10 minutes. If the second derivative of some function is positive on some interval, let's call it PQ, then f is concave up. If the second derivative is positive on some interval, then the function is concave up. All right, and this is the theorem. Do we believe it? Yeah. Okay, good. It's proved. All right. Well, so what should we do? Assume the antecedent. Yes. Let us assume that the second derivative is positive, and then what I would like to prove way down here is that f is concave up. F is concave up. But of course, concave up for me, not all textbooks, but for in our class, concave up means, what does it mean?
Pick up the elephant.
Tangent lines are below the function.
Tangent lines lie below the curve. So what I need to prove is that the tangent lines to f lie below f. The tangent lines to f lie below f. That's what I have to prove. Okay, what does that even mean? It's actually a little difficult to articulate what even is exactly intended by that sentence. Let's draw a picture over here. Let's draw some kind of concave up looking function on the interval PQ. Alright, what do we mean when we say the tangent lines to f lie below f? Okay, I'll call you. You raise your hand first. You.
So if you take the derivative at any point on that function, that will give you the slope of the tangent line. And then, so the function of like that, okay, so you know the slope of the tangent line and you want the entire equation of the tangent line. And so the equation of the tangent line is the derivative at that point plus the derivative at 0. Well, like y equals mx plus b. And then, so for any point that you plug into that equation, it'll be less than that point if you plug it into like into f.
Yeah. Okay. Yes. What Eob is saying is what we really mean when we say the tangent line lies below the curve is that given any particular point and its associated tangent line, it must be the case that for any x value whatsoever, if I try to plug that x value into the tangent line, the y value that I get is going to be less than the y value that I get when I plug the point x into the function. Does everyone see it? Richard, where it tells less than or equal to, I guess. Is that at a they're equal? Yeah. Okay, so if I want to prove that all the tangent lines to f lie below f, then I'm going to do sort of what I've already done, I'm going to pick an arbitrary point A. So pick arbitrary point A on the interval p comma q. And what I'm going to show about that arbitrary point is that the tangent line to it lies below the function. So I'm going to show the tangent line to f at x equals a lies below f. In other words, I need to show that that purple line is lower than my function. Okay, how should we do this? Well, I think what I'm going to do is I'm going to come up with an equation for this purple line. Right? So this is f. can somebody tell me what the equation, Ethan, what is the equation of this purple line? Right, Fleischman.
Y minus A equals,
Try again.
F of A.
oh, y minus f of A equals f prime of A times x minus A, times quantity x minus A.
Yeah. Yeah. That's just the generic equation for the tangent line to a curve anywhere. It's just the line with slope f prime of A, which goes through, is it recorded?
This.
Wait, was it the right class?
I have period. I just finished
Oh, cool.
adding up periods.
Okay, awesome. Yeah, so did you record them?
This? No,
Yeah,
not
can you
yet.
do
I
it?
just put it to the side.
Somewhere, yeah, somewhere, fine spot. Alright, so this is the line. Okay, so what I'm going to do is I'm going to temporarily call this a function g. And well, what is the g function? It's just f prime of a, x minus a, plus f of a. Cool? Okay, you're supposed to say cool. So, what I must show now, what I now must show, can somebody rephrase it again for me one more time in even simpler terms? What must I prove? That g of x is below f of x. Exactly. What I must show is that the g of x function is less than or equal to the f of x function on the interval pq. Cool? If I can do that, if I can show that given any x value whatsoever, I hit the tangent line before I hit the function, then that's true that the tangent line lies below the curve. And thus I've proven that the function is concave off according to our definition. Okay, so how can we show that? Well, let's just substitute in the thing that we're trying to do, right? So this is another one of those proofs where I just keep writing down what I want, and hopefully the inspiration will come to me. What I need to show is that f prime of a times x minus a plus f of a, I need to show that that is less than or equal to f of x. Following this? Taylor, you cool? Kind of cool? Okay. Is this starting to look familiar to some of you? I'm really tempted to do something now. Uses.
This is like, if you subtract f of a and then divide by x minus a, it's like the derivative.
Yeah. Uses says this is starting to look like all of that, you know, difference quotient, mean value theorem, blah, blah, blah stuff. Right? It turns out is all I need to do is demonstrate this inequality, then add f of a to both sides. That proves that this is true, and that. Okay, so it really all boils down to this statement. Can we prove this statement? And Musa said one more thing, which I didn't follow. I didn't do what he said this time. What else did he say to do? Yeah, Colin.
Divide by x minus a.
Divide by x minus a. Why might I not want to divide by x minus a just quite yet?
Because you haven't determined whether it's going to be positive or negative.
I'm not sure whether x minus a is positive or negative. Yeah, good. So that suggests that maybe we should do this with cases, right? So case one, this is one of our hardest proofs I think we do in differential calculus. Case one, let's suppose that x is greater than a. And now what I'm going to do is I'm going to draw x to be over here. So I'll like circle this in red or something so to connect it to the picture. So suppose that x is less than a, or greater than a. Well, if x is greater than a, then x minus a is positive, and so I can just divide by x minus a. And so I'll write down one more time. Thus, what is it that I want to show? What I really want to show is that the derivative at a is less than or equal to f of x minus f of a over x minus a. All right. Looking good? Or making sense? Okay, going a little bit fast now. How can I show that that is true? And hence, the mean value theorem is going to come into play somehow. because the mean value theorem is the only thing that enables me to connect what's going on with the function to what's going on with the derivative. Or maybe we should just talk about it for a minute. Which of these, is it obvious which one of these is bigger?
Especially the time graph.
Yeah, on this graph, which looks bigger? The average rate of change of f on the interval ax, or the rate of change of f at the point A? Which is bigger? Yeah, just look at it, right? Here, this is the rate of change at A, but the overall rate of change on the interval ax is going to be more than that. Why do I know that that's true? Besides that it just looks like it on my picture. Hint, what's the one major fact that we assume that we haven't even used yet?
Second derivative.
The second derivative is positive. What does that mean if the second derivative is positive? The derivative is increasing, right? The derivative is increasing. So of course, the derivative at the left end point of the interval is going to be less than the overall rate of change on that interval because the derivative is increasing, because the second derivative is positive. Okay, in the interest of time, I'm just going to finish this off. So here's what we do. We apply the mean value theorem to f on the interval ax. What does the mean value theorem say about the function f on the interval ax? Yeah? There exists a point C, you know, blah, 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 right? Yeah, there exists a point C on that interval ax such that f prime of C equals f of x minus f of a. Well, I guess I should do it the other way around. But it doesn't matter, because I'm going to do, well, whatever. It's f of x, okay, f of x minus f of a over x minus a. Yeah, sorry, yeah, just like that. Cool? Okay, so when is this point C? This picture's getting even more complicated. C is a point somewhere on the interval ax such that, let's see if I can even draw this. So this is the secant line through A and x. And C is a special point where on the interval ax where the slope of the tangent line equals the slope of the secant line. All right. My goal was to show that f prime of A is less than or equal to this, but since there's some particular point C that has this, what is it that I really need to show? I need to show that f prime of A is less than or equal to f prime of C. And that is just true. Why is that true? Because the second derivative is positive. True because the second derivative is positive. And by the definition of increasing, since f double prime is positive, the derivative is increasing. And if the derivative is increasing, as I move to the right, the derivative must be bigger. So I'm just going to write true because since f double prime is positive, f prime is